Well, the state of Texas is a real leader in what is called renewable energy. And by that, what I'm talking about is solar and wind. Faster than any other state, we have increased that source of electricity. However, it's still a very modest fraction of our total electricity usage in Texas. The trick is to maintain that source of energy and maintain the stability of the grid in the state. One of the issues then that we face in the Energy Institute is what we call baseload electricity storage. Can we come up with a way of storing the electricity from wind at night that during the day would enable us to meet our energy and electricity needs? This turns out to be a problem that we are working on, but that has no obvious immediate solution.
So if you wanted to pick a single area of technology that's important across the energy spectrum, energy storage is probably the largest and most significant one that we need to have success in. The technology to do that so far is pretty limited. Pump storage, compressed air, the ability to have batteries and other systems that can do that is important not only to these intermittent supplies, but it's important to meeting peak loads that can't be met, for example, from nuclear, because it does not scale up and down very quickly. So it's critical to enhance our traditional energy supply mix. It's critical to adopting more of the intermittent technologies like wind and solar that we want to depend on more in the future.
What the faculty here are developing are new concepts for batteries. For example, your battery at home, the copper-clad battery that you use for your flashlight or your iPod or some other device, has two electrodes. One is called a cathode, the other an anode. That's the silvery part on the outside. But inside, the electrolyte that separates those two electrodes is a liquid. What if you reverse that? What if you had a solid electrolyte, and instead of a metal or a piece of graphite, if you could make one of them a liquid, then you could pump that liquid into huge tanks. And so when the wind blowed, you would have electricity produced, and you would change that to chemical energy in that liquid electrode, and then you'd pump it up into a tank. And then during the day, when you needed the energy, you'd take that chemical energy back into your battery. It now becomes a fuel cell. In the building that I'm in, on the 8th floor, you would find John Goodenough, the inventor of the phosphate electrode for lithium-ion batteries. That has revolutionized those batteries, and they're the reason that they no longer catch fire in your laptop. If you go to Wikipedia and look up lithium-ion batteries, John Goodenough's name is on the front page.
Well, I'm John Goodenough, and I do research on transition metal oxides. In this electrolyte, which is a liquid, the lithium ions move from the anode to the cathode. It's got some problems with it as far as rate of recharge is concerned, but these batteries have worked very well for the wireless revolution, for your cell telephones, your laptop computers. So the question is, can we get a new strategy? The new strategy, we don't know whether it's going to work. We're just in the process at the present moment of trying to demonstrate the feasibility of this concept, and we'll see where it goes.
The application of batteries can be considered or classified into three types. Portable applications, that's laptop, cell phone. Vehicle applications, that's the car application. Stationary storage means storing wind energy and solar energy and using it. For cell phone and laptop portable applications, you usually need slow discharge, slow charge. That's okay. For vehicle application and solar energy storage, you need fast charge, fast discharge. How fast you can charge, how fast you can discharge your battery depends upon the ionic and electronic diffusion or movement in the material, solid material like this. The materials are composed of atoms, and they are all arranged in a particular fashion. That's called a crystal structure. So in those structures, how the ions and electrons move is what is going to determine the charge-discharge rate. So we use our basic chemistry and physics knowledge to design such materials.
So it's a concept, the liquid electrode, the solid electrolyte. It sounds straightforward. It turns out it's very tricky to create an electrolyte that's solid that will do what I've just described. But that's what we do at universities. We do the basic research to see if we can find a way to produce that electrolyte, solid, that will then enable us to store enormous quantities of electrical energy from when it's produced from wind at night to when it's needed during the day when it's hot.